All right, this is the Math 136 Exam 1A review. This is to help you guys get prepped for this first unit test, and there is a 1B version of this same review that is for you to try on your own. So for all of the exams this semester, I will do videos for the 1A version. So we're going to start off with what is the most important things that you need to know about each problem and how do you work them out. The most important thing that students can do to prep for a test is not only make sure you know how to do steps, because a lot of students just focus on the process. Oh, I just need to do these steps. You need to know from reading the directions what steps are appropriate and what should you do first. So for this first one, the directions are to simplify and assume all the variables are positive. Now, when we say simplify, that usually means that we're trying to make something reduced or in a smaller format, not really a smaller number, but a more readable format. Like when we talk about fractions, 4/8 is simplified if it's 1/2. For like terms, it means we add the like terms together. So for radicals to be simplified, you have to take any perfect powers outside of the radicand. And remember, the radicand is the part inside. So when we look at this, we would look at the number first, and we would ask, since this is a square root, we would ask, are there any perfect square factors of 75? So 75 can be written as 25 times 3. So a perfect square is 25, so we can actually break this up into that. Now we could think 75 times 1, but that doesn't help us. So you're looking for factors that have a perfect square for one part and a non-perfect square for the other. So I would rewrite this as the square root of 25 and then times 3. And then I also have the x to the 12th and the y to the 20th. So when we take the square root of 25, because now that this is a factor, we can take the square root of it, that would just be 5. So we have a 5 on the outside of our radical. Now the square root of 3 is not going to go away because that's not a perfect square. So it's going to still be inside the radical. When we look at our variables, it's understood that there's a 2 when you talk about a square root. So we're really asking the question when we're talking about repeated variables, how many groups of 2 are there in x to the 12th? The number of times that is answered that it goes into it, that's going to be how many x's we pull outside of the radical. If there's a remainder, that would be how many there are left inside. They weren't able to group up into a pair. So since 2 goes into 12 evenly, that would be 6. So x to the 6th. Now, because they said all variables are positive, we don't have to worry about putting an absolute value on this. If you have an even root, remember, if they don't tell you the variables are positive, you sometimes have to put absolute values on things that are not naturally positive when you pull them out. So we're okay here because we do have all of our variables are positive. And then we'd say, how many times does 2 go into 20, or how many groups of 2 are in 20? And that would be y to the 10th. So there's the only thing going to be left in the radical is going to be the square root of 3. Everything else came out as perfect squares. Okay, let's look at another one. So simplify for the cubed root one. Notice they didn't tell us the variables are positive, but with cubed roots, it doesn't matter. Odd roots do not need to have the absolute value anyways. So when we look at this, we're trying to figure out perfect cube that goes into 108. So if you're not sure off the top of your head what that perfect cube would be, sometimes it's good to make a list of perfect cubes. So 1 cubed is 1, 2 cubed is 8, 3 cubed is 27. Obviously, you can use your calculator to help you figure this out. 4 cubed is 64. And I know it's not 5 cubed or anything bigger because that's already bigger than 108. So you would take just a calculator. So this is how you would figure out what your biggest perfect cube possibly that could go into 108 is. And I always start with the biggest one that I've got that's under the 108. And I just see if it divides evenly. So 108 divided by 64. And it doesn't go evenly, so it's not 64. Then I would try 108 divided by 27. And that's 4, so it does go into it. So this can be broken down into the cubed root of 27 times 4. And then we have our x to the 8th and our y to the 10th. And we're going to do the same steps we did up above. So this time we say the cubed root of 27 is 3. You can't take the cubed root of 4, so that's just going to be stuck inside the radical because that's not a perfect cube, and it doesn't have any factors that are perfect cubes. 3 going into 8. So how many groups of 3 are in 8? Well, 3 goes into 8 2 times evenly, so that would be 2 x's we're going to pull on the outside, and 3 times 2 is 6, so that means we would have 2 left over to make it up to 8. So we're really just doing division there. And then 3 goes into 10 3 times evenly, so we'd have a y to the third on the outside with 1 left over. So there's a y to the first on the inside. So there's our answer for number 2. Okay, so switching gears, number 3 is, it's still a radical because I see a 1/3 power on the outside, but it's been written in rational exponent form. So we're going to talk about this one for a second. There's a couple different ways you could approach this. If everything is inside of a parentheses, I think it's easier to reduce that parentheses first if you can, than to worry about the power on the outside. For example, -24 divides by 3. So if we divide that, that would be a -8. It's still going to be on the top because think about 3 going into 24, so it's still on the top. And then we can reduce some of these x's. So since we have 61 on the bottom and 34 on the top, that's going to cancel out and leave with 27 on the bottom. So that will be x to the 27th on the bottom because there's more x's on the bottom. And we still have our y to the 9th on the top. Now, because this has a -1/3 power, I don't want to jump straight into turning this into a cubed root. When we do that, we like our exponent to be positive. That's how we need it to be for us to convert that. So one thing we can do to make that exponent on the outside positive is we can flip the entire fraction. We are changing everything's location. So this would be x to the 27th over -8y to the 9th, all to now the 1/3 power, the positive 1/3. Notice none of the signs of the exponents inside changed. This is still -8. It should still be a -8. It's just in a different location. So now we can take the cubed root of everything, because remember 1/3 power means cubed root. So this would be the cubed root of x to the 27th over the cubed root of -8y to the 9th. This, remember, is not, we're not asking the cubed root of 27, we're asking how many groups of 3 are in 27 since that's an exponent. So that's going to be x to the 9th. And then we are asking the cubed root of -8 because that's just a number, so that would be -2. And then 3 goes into 9 evenly 3 times. So if I rewrite that, that would be -x to the 9th over 2y to the 3rd. Okay, let's look at number 4. For number 4, we're trying to rationalize the denominator. So to rationalize a denominator means to have no radicals in the denominator. Right now we have a radical 3, and it's a binomial. So the only way to get rid of a radical in a binomial is to multiply by something called the conjugate. The reason that works is it creates a difference of 2 perfect squares factoring, essentially. So when we FOIL it out, we get 2 perfect squares. And perfect squares, remember, will come outside of the radical. So the conjugate, the thing that you need to use, is you keep this binomial except you change the sign in the middle. So we're going to multiply this by 7 minus the square root of 3. And whatever we do to the bottom of the fraction, we also must do to the top, so that we're really multiplying by 1. So then this would be 8 times 7, which is 56, and 8 times -1, and then we have the square root of 3, so -8 on the square root of 3. The bottom, we have to FOIL or distribute this out. So 7 times 7 is 49. 7 times negative square root of 3 is -7 square root of 3. Notice we don't make that 21 because this is an outside number and that's an inside number. And then 7 times positive square root of 3. So notice these are going to cancel. And then finally we get a positive times a negative, and square root of 3 times square root of 3 is square root of 9, and I do know that that will reduce, so I'm going to work that out next. So this is 56 minus 8 square root of 3 over 49 minus 3, because that is the square root of 9. Got ahead of myself writing. So my bottom actually reduces down to 46. Now we need to talk about whether or not your answer is in reduced format or not. Because every single number on the outside is divisible by something, they actually aren't reduced right now. The way that I like to teach this is that if you can factor something out of the top, then you can cancel it with stuff on the bottom. So the question is, what do we want to factor out? Well, we know that 8 and 56, I believe 56 is also divisible by 4, and it's also divisible by 8. So you could pull out an 8, but that's not going to help us if it's not going to divide into the 46 evenly. So 46 is not divisible by 8. 46 is not divisible by 4, but 46 is divisible by 2. So it looks like everything on top and bottom have a common factor of 2. So if we pull a 2 out on top, we're just cutting things in half. So that would be half of 56, which would be 28, and then half of 8, which would be and it's still negative, so negative 4 square root of 3, and then that's all over, and I'm going to pull out a 2 down here, and that's going to be 23. So now that we have a 2 out front in both, we can cancel those out. So my final answer is 28 minus 4 square root of 3 all over 23. Now, all of the outside numbers do not have the same common factor that can be pulled out. Okay, so let's look at number 5. Number 5 says factor completely. If the polynomial cannot be factored, write prime. Remember, factoring completely means that we want to break this into a product of binomials or monomials so that nothing inside each binomial is a common factor, and we have nothing that factors further. So you can't leave something that would still factor again. So we're looking at a trinomial, and it has a non-1 in front. So the typical method for this is the AC method or factor by grouping. So the way we start that off is that we multiply the A term, which is 3, times the C term, which is negative 28. Now, I do include my negative sign. Not everyone does. That helps me with my factors that I'm going to list. So that's going to be negative 84. And then I list factors of negative 84. Now, I'm going to need a little bit more room for this one. So for negative 84, I just start with 1, and I just list 1 times what? So 1 times 84. 2 times 42. I asked myself, does 3 go into it? I divide it by 3 to see. 3 and 28, which I knew that because that's what we got it from at the beginning. And then 4 and 21. Okay, we just keep going. If you find the pair that works, you could go ahead and stop, but it's better just sometimes to make the whole list just to double check. So 5 doesn't go into it. Does 6 go into it? 6 and 14. You'll notice that this gap is getting closer and closer together. So I would check 7. 7 and 12 work. As long as nothing between 7 and 12 works, we would know we'd have our whole list. So we could try 8, which doesn't work, 9, which doesn't work, 10, which doesn't work, 11 doesn't work, and 12 we already know works. So we've got the whole list. Now, because this multiplied to make a negative 84, we want different signs because it's going to actually subtract to the middle, not add to the middle, because it has to multiply to make a negative. So it looks like 21 and 4 can make 17 if we subtract. And it's a positive 17, so we want a negative 4 and a positive 21. Once you've determined your pair, you take them over here and we do what's called expanding the middle. So the first term stays the same, the last term stays the same. You never change those. What we then do is separate 17 into a negative 4 and a 21, and they both have the same like term here, so they're going to both have x. It doesn't matter which one you write first, but I always try to put it easier on myself. I'm going to put 21 closer to 3. And then put the negative 4x closer to the negative 28. It should factor the same if you're careful with your signs. So if I look at the first pair, we're factoring by grouping now that this is 4 terms. I can pull out a 3 and an x. If you divide that out of both of those, that would leave you with an x and a plus 7. If your second pair starts with a negative, you have to pull that out, and then they both are divisible by 4. So we're going to pull out a 4 with that. So then we're dividing both of these by negative 4. That's why this sign will change to a positive, because negative 28 divided by negative 4 is actually positive 7. If you have a matching binomial, that means that this continues and factors. So x plus 7 is like a GCF for the whole thing. We pull it out to the front. The leftovers are what would be left if we pull out the x plus 7s. So that's going to be a 3x and a minus 4. And that is the factored form for this one. Notice that x plus 7 has nothing in common, 3x minus 4 has nothing in common. So we know we've completely factored those binomials. Okay, let's look at number 6. So factor completely, again, if the polynomial cannot be factored right prime. So this time we're not dealing with a trinomial, we're dealing with a binomial. When you're dealing with a binomial, there's some techniques that you want to try. The first thing you want to check is to see if it has a GCF. That's always what we should check for any polynomial that we're looking at. If that doesn't happen, then if it's a binomial, the only two options for factoring are perfect squares with a minus sign between them, or a difference of two perfect squares, or a sum or difference of two perfect cubes. If it's the perfect cube method, then it's going to factor into a binomial and a trinomial, which will show you the pattern when that happens. If it's perfect squares, then it factors into two binomials, and we'll show you the pattern for that when we get to it. So let's look at this first one. This is a binomial, and it doesn't have a GCF. And we know that 27 is not a perfect square, and neither is x cubed, so it's not going to be perfect squares. But 27 is a perfect cube, and x to the third is a perfect cube, and 64 is a perfect cube. So all of them are perfect cube, which means this is a candidate for the perfect cube method. To factor perfect cubes, you have to find the cubed root of both bases. So this is asking, what would this be before we cubed it, and what would this be before we cubed it? So the cubed root of 27 is 3. The cubed root of x to the third is just x. The cubed root of 64 is 4. Once you've determined that, you're going to be following a pattern. So the way that it factors is you have a binomial, and then you have a trinomial. The two roots are going to go into the binomial, that's the 3x and the 4, and you keep the sign of the original problem. So this is going to be 3x minus 4. So that's the easiest part. So the next part is you're going to take 3x and 4 and you're going to pair them in a specific order to make the trinomial. The first pairing is you times the first root times itself. The second pairing for the trinomial is we times the first root times the second root. And the third pairing is that we times the second root times itself. Now the formulas in the textbook, they go through and they call it a squared, ab, and b squared, but I find that if you talk about pairing, that seems a little bit easier and students are less likely to miss the coefficients. So 3x times 3x would be 9x squared. 3x times 4 is a 12x, and 4 times 4 is a 16. Now notice I don't have any signs in here. The way we remember our signs for the perfect cube factoring is a little phrase called SOAP. We already did the S. The S stands for same as the original. The O stands for opposite to the original. That means the original problem. And then the AP stands for always positive. So notice this was same as the original, which was a negative. Opposite to the original would be a positive, and then always positive. So there's only going to be one negative sign in these perfect cube factorings. It's either going to be in the binomial or the first spot of the trinomial, the first in-between spot. That's how we factor it. So that is the final answer for the factoring of the first perfect cube that we have here. Number 7 is also two perfect cubes. This would be 2 and a y cubed, and the cubed root of 125 is 5 cubed. So we're going to do the same thing. This would be 2y plus 5 because we keep the original sign. Then we have our trinomial, and we're going to do the first times itself, the first times the second one, meaning our roots, and the second one times itself. So this would be 4y squared, 10y, and 25. And then we do our signs. Same as the original, opposite to the original, always positive. And that's how that one factors. All right, let's look at number 8. This one again is a factoring problem, factor completely. But this time we're starting out with, it looks like 4 terms. So you still want to check for a GCF first, and I do believe there is a GCF that we can pull out of all of these, but we're going to double check. There may not be actually. So let's look. So we're going to look at 5 and 75 and 72 and 108. Actually, no, there is not a GCF that we, yeah, since there's not a GCF that we can pull out, we can go ahead and go to factor by grouping, but you should check that first. So there is not a GCF for all 4 numbers. So since there's not, we're going to go straight into factor by grouping. So I'm going to look for a pair of GCFs. In other words, a GCF for the first pair and a GCF for the second pair. So 50 and 75 are both divisible by 25. That's the largest thing that goes into both of them, and they both share at least 2 of the x's, so x squared. If we pull that out and we divide it out of each piece, that would leave me with 2x and then plus 3. The second pair leads with a negative, so we have to pull that out, and then we have 72 and 108 are both divisible by 36. I had to take my calculator and do that for a second ago. So that's 36, and if we divide that out, that also leaves me with 2x and plus 3. Now, since that's a matching binomial, that comes to the front as part of my answer, and then remember the leftovers make my other answer, so 25x squared minus 36. The problem is this is not completely factored. This is why I said sometimes you do have to double check your final answer. The 25x squared minus 36 is perfect squares with a minus sign between them. So this is the difference of 2 perfect squares. So when you have that, remember it factors into 2 binomials. So just as a refresher, so 25x squared minus 36, this would be 5x squared, and this would be 6 squared. With perfect squares, you get a binomial and a trinomial with both roots, or sorry, binomial times binomial. I'm trying to talk and write. So binomial times a binomial, and they're exactly the same except one has a plus in the middle and one has a minus. If you FOIL that back out, that makes sure that the middle terms cancel when you FOIL. So this is going to factor again, so our final answer here is going to be a 2x plus 3, and then the perfect square factors into the 5x plus 6 and the 5x minus 6. So there's my final answer for number 8. Okay, let's look at number 9. For number 9, we're looking at a division problem with a lot of different polynomials in it. So our technique for division, when we simplify, is that we first turn it into a multiplication problem by multiplying by the reciprocal of the second fraction. Then we factor everything, and because everything will then be multiplication on top and then everything is multiplication on bottom, any common factors can be canceled or reduced out. So that's what we're going to be doing. So the first step is to rewrite this as multiplying by the reciprocal of the second fraction. So we keep our first fraction the same. We flip the second fraction after we make the middle a times symbol. Next, we want to factor each of these pieces. So on this first trinomial up here, we're looking for factors of 3 that add to 4. So that would be positive 3 and positive 1. I'm going a little bit faster with the factoring on these. For the bottom, we're looking for, since this is still a 1 in front, we're looking for factors of 18 that add to negative 9, since this is positive. So that would be a negative 6 and a negative 3, because they multiply to positive 18 but add to negative 9. For the bottom of this one, because x minus 6 is not going to factor, it's just a binomial, no perfect squares or perfect cubes. The bottom is we need things that multiply to negative 12, so they're going to be one positive and one negative, but they add or subtract to negative 1. We can think of it as subtraction. So this is going to be an x minus 4 and an x plus 3. Now, if you've done this correctly, you'll notice that you have x plus 3, x plus 1, and x minus 6 are all the things across the top. You do not need to distribute this out. And then on the bottom, we get x minus 6, x minus 3, x minus 4, and x plus 3. I'm running out of room. Since all of this is multiplication, any common factors like the x plus 3 can cancel out. There's also an x minus 6 on top and bottom. So this becomes just x plus 1 on top over x minus 3, x minus 4 for our final answer. Okay, let's look at number 10. We're looking at adding with two fractions. When you're trying to add or subtract, you have to get a common denominator. So we need to figure out what our LCD is going to be. So the LCD, it has to be something that we can turn both denominators into. So 7 and 5 both go into something bigger. They go into 35. I have two x's on this side and 3 on this side, so we need to make the smaller one into the bigger one. So we're going to go with x to the third. And then we have 2 y's on this side and 4 on this side, so we're going to make it the bigger case of y to the fourth. So that's going to be the common denominator that I'm going to strive for on each fraction. What you do next is you take those fractions and you multiply by what's missing to make this bottom happen. So to make 7 turn into 35, we multiply by a 5. We already have the x to the third, but we need 2 more y's, so we're going to multiply by y squared. Whatever you do to the bottom of a fraction, you have to do to the top to stay consistent so that we're multiplying by 1. And then for the second fraction, we have 2 over 5x squared y to the fourth. So we need to multiply the bottom of this fraction by something to make it 35, so that would be a 7. And then we need to make the x an x to the third, so we need another x. The y to the fourth is already what we want. So we're going to multiply this by 7x on top and bottom. Once we work out the tops, this is going to be 20y squared plus 2 times 7x would be 14x, all over 35x to the third, y to the fourth. Okay. Now you want to double check here at the end. There's no common factor that you could pull out that would cancel with something on the bottom. Now we could definitely pull a 2 out of the top, but 2 does not divide evenly into 35, so it's not going to help us to pull that 2 out. Okay, let's look at number 11 next. We're still simplifying. This time we're subtracting 2 fractions, and their denominators are a little bit more complex, so we need to factor both of them. This is 2 perfect squares with a minus sign between them, so this would be the 2 square roots, once with a plus and once with a minus. Factors of 20 that make -9 when we add them together would be a -5 and a -4. So it looks like we have a common factor of, they both have the x minus 4, but each of them is missing something that the other has. So we're going to include those other 2 binomials as part of our denominator as well. Remember, we can't take something away, but we can multiply it into the new denominator. So all 3 of these are going to be part of our denominator. So we take our first fraction, and I'll try to use color this time to emphasize what we're putting in. Go ahead and leave it in factored form, and I'm going to multiply this one by what it's missing. It's missing the x minus 5. So whatever we do to the bottom, we must also do to the top. And then we have our minus sign, and then our second fraction. This one has the x minus 5 and the x minus 4, so it's missing the x plus 4. And we do whatever we do to the bottom, we also do to the top. So we're going to work this out. Now I recommend, and not everyone does it this way, but I actually recommend that you write this as one big fraction with just copying the top from left to right, then distribute. That's just so that you don't lose that negative sign and make the mistake where you end up losing it and you don't distribute it correctly and your whole answer on top gets messed up. So this is 3x minus 5 minus 7x plus 4. You can't cancel the x plus 4s and the x minus 5s right now. First of all, that's only true if everything on top is being multiplied together. Right now we have subtraction on top. So what we do next is we clean up the top. So we distribute these things. And notice this negative is getting distributed with that 7. So this would be 3x minus 15 minus 7x minus 28. All over our LCD. And then if we combine our like terms on top, 3 minus 7x would be negative 4x. Negative 15 take away 28 is going to be negative 43. And then we bring down our denominator. Notice we're not getting any kind of solving here. This is not solving an equation, it's simplifying. So we should be getting something that is just a reduced fraction or ratio. The negative 4 and 43, there's nothing we can pull out that they have in common, and they don't match the binomials on the bottom. So that is our final format. Kind of block that off. Looking at 12, there's a couple different ways you can attack these. You can get a common denominator on top subtract the fractions, common denominator on bottom, subtract the fractions, and then you could multiply the top by the reciprocal of the bottom. That's one attack method. Another one, and the one I'm going to show you on here, is to try to clear it out by using the LCD of all the little fractions. So if you think about each of these being over 1, the little fractions are 1, denominators are 1x, 1, and x squared. So the LCD of all those little denominators would just be x squared. We take the bigger one of the two if they're the same. So if we multiply everything on top and everything on bottom by x squared, it's really like we've multiplied the whole top of this big fraction and the whole bottom of this big fraction by x squared. So this would be 4 times x squared minus 1 over x times x squared over 16 times x squared minus 1 over x squared times x squared. This should cancel out some of our denominators. In fact, it should cancel out all the little denominators. So this is going to just be an x, and this is going to be gone and just be a 1. So now I have 4x squared minus x on top over 16x squared minus 1 on bottom. The trick to getting this one right is knowing that that factors again. I'm going to give myself a little bit more space. Oops. Hang on just a second. There we go. And I'll have to fix that denominator answer of that other one in just a second. So this is going to be, what can you do with the top? Well, it's not perfect squares, even though 4x squared is a perfect square, but x to the first is not. So it looks like the only thing I can do on top is pull out a GCF of x. So that leaves me with an x times a 4x minus 1. The bottom is two perfect squares. This is 16x squared, which is both perfect squares, and 1 is a perfect square as well. So the square root of 16x squared is 4x. The square root of 1 is 1. So this is 4x plus 1 and 4x minus 1 because it's the difference of two perfect squares. By doing that, we now have a matching binomial on our top and bottom factors. Remember, we cancel the factors out that match. So my final answer is x over 4x plus 1. We do not cancel the x's here. This is a monomial. This is a binomial. They do not partially cancel like that. All right, so that's the end of number 12. And I'm going to really quickly fix the answer that got scooched down a little bit. So this was x plus 4, x minus 4, and x minus 5. Okay, I'm going to do number 13, and then this will be the end of part 1 because the review is so long. I will be doing a part 2 and maybe even a part 3, so it might be more than one video. But just to kind of get to a good stopping point, this is the last of the simplifying problems before we get into solving. So for this one, this is what we call the big factoring problem. And a lot of people struggle with this one because there's just so much to look at, I think. There's a lot of pieces that are all kind of just all jumbled together. The key thing I like to point out is that there's a plus sign in between this blob on the left and a plus sign right here, kind of separating it from the blob on the right. So this is like blob plus blob. If we could find a GCF for those two things, we could pull it out to the front of the whole binomial blobs, okay? Now, I know those are not technical terms, but sometimes that helps if you just think of it as very simplistic. So the first thing I like to have students do is if you find any monomials on a same blob together, go ahead and try to multiply them together. We can't just FOIL all this out because these are raised to powers. So 2 times 4 is 8, and then I bring everything else down. This will just clean up a little bit of what we're looking at. And that's a 3. And then on this side, or this part of the plus sign, there's a 3 and a 6. So we can multiply that together and get 18. And then I like to make sure I write it in the same order. So the x minus 5 is going first, and the 2x minus 3 is going second. Okay, so now we want to look at this piece by piece. So 8 and 18 are both divisible by 2. That's the largest thing that goes into both of those. And then for the x minus 5 to the 9th and the x minus 5 to the 8th, they have 8 of those in common. So we'll pull out an x minus 5 to the 8th. And for the 2x minus 3s, they have 3 on this one and 4 on this one. So they have 3 in common. So this is going to be my GCF that I'm pulling out to the front. That means I'm going to be left with a bracket and some things left inside that didn't get pulled out. So you just divide each of these out. So 8 divided by 2 would be 4. X minus 5 we have to the 9th. We take away 8 of those, we would still have x minus 5 to the 1st. we took out all 3 of the 2x minus 3's to the third. So all of those are gone in the first one. Plus 18 divided by 2 is positive 9. We had 8x minus 5's. We divided all of those out. And we have 2x minus 3 to the fourth, but we only divided out 3 of them. So we'll still have a 2x minus 3 to the first. Okay, so then we're on what's called cleanup crew. You're going to work on the blue part and clean it all up. And the red part's just going to stay out front. So it's just part of my final answer. And then this would be 4x minus 20 plus 18x minus 27. And we can add some like terms in there. So let's do that. So 4 plus 18 would be 22x, and negative 20 take away 27 more would be negative 47. You do want to double check that the binomial at the very end does not have a GCF, because it is possible for there not to be a GCF at the beginning that was bigger than what we had. We only had a 2 that came out, but you could, by pulling things out and then distributing and combining like terms, there could still be a GCF between the two numbers, but 22 and 47 have nothing in common. So that's my final answer. And that is going to be the end of the part 1 of Review 1A.